talk about a drafting detector, something that you need if you were bike racing in a triathlon. So I'll present Team 5, QuikiTrak.
Hello everyone, I'm Shawn, Doria. This is Takao, Pavel, Andy, and Karen. We're Team 5, the QuikiTrak team. Our project is the drafting zone detector for triathlons, and our customer is Professor Carruthers. So what's drafting? In the bicycle portion of a race in the triathlon, there's no drafting. In the bike portion of the race, when one racer is behind another racer, he receives less air resistance, thus gaining an unfair advantage in the race. So to prevent that, they implemented a rule that states that you cannot stay behind another bike within 7 meters for over 15 seconds, otherwise that would be considered a drafting violation. Right now, the way they detect drafting violation is to have someone watch the race, which is both inefficient and inaccurate. So our goal, our project, is to create a lightweight sensor device that can be mounted on each bike that will be able to detect drafting violations both efficiently and accurately. And there will be a software, and the device will be able to store the drafting violation and later upload it to the software for the race director to see and then decide whether the drafting violation is valid or not and punish the athlete accordingly. So here are our requirements for the project. We separated according to each individual module for our device. So for the enclosure, the device has to be lightweight and small, hence the weight limit and the dimension. The battery has to last for the duration of the race, since we don't want the device to go off during the middle of the race. The distance sensor has to detect the 7-meter drafting zone as well as the 15 seconds draft time in order to record a draft violation, which will be stored in the processor's flash memory. And the wireless communication will be used to transfer the data from the device to our software, which will store the data in a database and later display it to the race director after the race. And now I will hand it over to Takao, who will go over the overview block diagram device.
All right, this is our high-level system block diagram. There's a computer which has our software. There's an enclosure that has all of our electrical components, and there's also a front and back sensor. These two sensors are powered by a lithium-ion battery of 11.1 volts. Before the race, the user is going to use the computer and its access point to wirelessly pre-program a unique ID to this device. And during the race and throughout the whole race, this back sensor is going to be sending a pulse. That pulse is going to be the ID that was pre-programmed onto this device. The front sensor is going to be trying to receive the pulse throughout the race. Like Shawn said, there's a 7-meter drafting zone. And so when a bike enters this drafting zone, this sensor is going to pick up a ID from a different bike. It's going to store it into the data processor and then start a timer. And it's going to record the starting time and ending time of the draft violation. After the race, the user can then pick up all this information wirelessly back to the computer and then process and sort this back. This is a diagram of the bike. There's going to be an enclosure in the middle of the bike, and then the two sensors, one in the front and one in the back. And here's a picture. Here's the enclosure, and that's what the sensor there. They have been to Pavel for the
So basically in this diagram what we have is the board that we created to modulate the sensors and also to receive the signal coming from the emitter. If you look, the processor that we're using is the MSP430. So as you see, it has 2 pins going to an inverter. The reason for the inverter is to, what ends up happening is we actually are using a Schmidt trigger, but optical coupler, but it's an inverting optical coupler, so we need an inverter to invert that signal again in order to restore the proper polarity. And the reason for the optical coupler is because we have 2 power sources. We have an 11.1 volt power supply for the sensors, and we have a 5 volt power supply for the MSP430, which is the microcontroller that we're using. The optocoupler is over there, and that goes to the transistor, which is used to amplify the signal coming from the MSP430 in order to drive the emitter. Now, on the receiver side, what we have is we receive the signal from the receiver, and that goes also into an optocoupler, which then puts down the voltage to 5 volts from the 11.1 volts coming out of the receiver. And that then goes into the microcontroller, which detects the traffic violations. The sensors that we're using, they're Banner Engineering 18 sensors. They're opposed infrared sensors. So they're a paired emitter and receiver that operate at a modulated frequency so that there's no interruption from background noise or from other nearby RF sources or infrared sources. If we look here, the way that the drafting works is the emitter is constantly outputting a drafting signal, and the receiver is constantly detecting. Now, since the front sensor, which is the receiver, is constantly looking for the ID from the emitter, when we finally do get an ID, for example, the device says, hey, we've received an ID, and if it sees that ID for 15 seconds, then we'll have a draft violation. If it doesn't see that ID, then it'll just go back to the normal mode, constantly looking for an ID and saying that, hey, we're not receiving any signals, so thus we're not having any traffic violation. The way that we detect the 7-meter length is actually based off of a power argument. So when the power reaches a certain threshold, we know that it's less than 7 meters, the two receiver and emitter, or the drafter and draftee. Otherwise, it's greater than 7 meters, and we don't detect drafting. I'll now hand it off to Andy, who will talk about the software.
So next we have the software, and when the user first opens the application, we prompt them for a username and password, and we use the MD5 password encryption to encrypt the user input and compare it to a value in the database. And after that, we let them actually use the software. We give them some wireless functions, so we could download or set the user of the device. To do this, we have a MSP430 connected to the computer via USB, and has a UART for serial communication. So the user gives a request, but it goes to the access point and it sends out a wireless message via Simplicity, which is a Texas Instruments developed wireless protocol. After that, they can download all the drafting violations, which is stored in the database, and the user can then perform SQL queries to the server to do sorts or searches for the violations that they want to get. This is what we're storing in the database. We have the user ID, the drafter ID, last name, first name, and the times of the draft. And at the time that we download the data, we actually determine if it's a draft or not. We'll compare the total time to 15 seconds to see if it's greater or less than. And that right there, second valid draft, is what we use to determine if the cyclist performed the draft. And now Karen will go through the rest of the software.
So the user interface of our project is provided for the race director to view and manage the drafting violation data in the database. There are 8 event handlers that we implemented in our software. The first one is detect device. It can detect devices currently in the area and display them in the list. The user can also program the ID number of the cyclist into the device. The user can also download or delete data if they wanted to. So they just click on the download data button, so they can download the data from the selected device and store them into the database. Or they can clear out the data by clicking on the device delete data button. So we also provide